All right, we are live. Audio and video is up. Welcome back to Statics. Only 3 more content lectures, and this is one of them. Now, let's talk about some housekeeping. So you all turned in 6.3 today. Homework 6.2 should be graded. Let me check and make sure here on Blackboard that that is correct. We should already have the grades posted. Yeah, the grades are posted. So let me check and make sure the solution is live. I think on a couple lectures ago, I said the solution was live and then it wasn't. Okay, so let me go ahead and make that available. Okay, so all the solutions are available up until 6.3 that you just turned in today. We'll try and get that graded as soon as possible. 6.4 is your next homework assignment, and it's your last one before the exam. I went ahead and gave you one more practice problem on shear and moment diagrams. That's going to be due Monday. What'll happen on Monday is we're going to have our exam review. The exam is going to cover pretty much everything past exam 2, so centroids, trusses, and shear and moment diagrams. So come prepared Monday with questions. Come prepared, ready to ask questions about about what we're doing here. I'll have a set of review slides posted. Hopefully, I'm going to try and do that today with all the relevant formulas and equations and whatnot. But I thought it was a good idea to have practice on this sort of final topic with shear and moment diagrams. I'm really only interested in an introductory statics class that you're able to handle concentrated loads and distributed loads. I know you civils, when you take me for structural analysis, will handle far more than that. Okay, so let's get right into it. What I want to do is I want to start off by just recapping the basic relationship that we derived between loads, shears, and moments. And so the idea is that if you have your loads, essentially what you're doing when you draw the shear diagram is you're sort of integrating the load diagram, or the free body diagram, if you will. You follow your reactions, right? You say, okay, I'll draw, I have a 40 kip reaction here, so I'll draw, upwards 40, and then I'll, follow that stair-stepped pattern with the loads to draw the shear diagram. You're basically integrating that to draw the shear diagram. And then once you have your shear diagram, you determine the area of the shear diagram, and so you're integrating the shear diagram to generate your moment diagram. And then you can use the flip side of that relationship to ensure that your values make sense. So our moment diagrams from the last lecture were linear, and the slope of those linear portions matched the values on the shear diagram. And so that was really sort of the relationship I wanted to explore in the last lecture. And today what I want to do is I want to extend that a little bit further by talking about distributed loads. And this is just saying everything I just said. I guess I skipped ahead a little bit talking about the graphical approach. So between load and shear, at any given point, the slope of the shear diagram is equal to the load, and the change in shear is equal to the magnitude of the load between those points and what have you. And the same thing with the moment diagram. All right, let's talk about distributed loads. So we've handled distributed loads before, and we've done something like this. So we take the distributed load and then we idealize it as a single point load, or a single concentrated load. The magnitude of that load is sort of like the area under the load. So, for instance, if we have, this is a uniformly distributed load. So it's, let's say we have, like 3 kips per foot over a distance of, 15 feet. So the magnitude of that load would be 3 kips per foot times 15 feet. So it'd be 45 kips. And then we would place that single load at the centroid. So the resultant of that load acts through the centroid. Now, here's the kicker, and this is something you really have to sort of train yourself to do, is that this is great when you're computing the support reactions. But when you're drawing the shear diagram and you're drawing the moment diagram, this idealization is something that you and I are doing to make the reaction computation easier, but it's not the real life loading on the beam. In other words, we can turn it into a point load to determine the reactions, But when we're drawing the shear diagram and drawing the moment diagram, we have to revert back to that distributed load. It has to, the shear diagram and the moment diagram are representative of the real loadings on the structure. And so that's an easy thing to get tripped up on as you're drawing the shear diagram and the moment diagram, because if you keep it as that distributed load, what can happen is you can start at 0 and end at 0, and so you'll think you've done it right, but it's actually wrong because you didn't use the original loading. So it's something you definitely want to keep it in the back of your head, that once you're done with those reactions, you go back to the original loading. Now, the next thing I want to make sure that we're clear on is that integral relationship. So whenever you're dealing with a distributed load, things change a little bit with the shear diagram and the moment diagram. See, when we drew our shear diagram in the last example and draw the moment diagram, what we got for the shear diagram was this sort of stair step sort of graph, and then the moment diagram was a bunch of linear segments that were all connected together. So from a math perspective, the shear diagram had a slope of 0, so they were constant functions, and then the moment diagram was a sequence of linear functions. So you had constant functions for the shear diagram, and you had linear functions for the moment diagram. Well, a distributed load ups the order by a magnitude of 1, because now you have a constant load. Instead of 0 load, you have a constant load. So if you integrate a constant, what do you get? You get a line. So the shear diagram is linear, and therefore the moment diagram is quadratic. So you're going to have rounded, or not rounded, sort of parabolic functions of the moment diagram. So it's something that you've got to be aware of when you're drawing it. It's really not that hard once you understand a few graphical cues to be aware of. And we'll walk through this as we do our example today, because this is actually pretty straightforward. What I have found that's hard among students starting to look at this is not the drawing of the shear diagram or the moment diagram, or the concept behind what it should look like. That's usually pretty easy to grasp. What's hard sometimes is just the basic geometry. We're going to have shear diagrams that look like this. And what I don't want there to be an issue with is some of the geometry challenges that will arise. So for example, let's take this. This is sort of a snippet of a shear diagram that I came up with. And we're going to have shear diagrams that look like this when you're attacking these types of problems. And so the question is, how do we determine the area under these triangles, or more specifically, I guess, how do we determine the base of these triangles really easily? And so I'll show you real quick. Let's go back to some really basic stuff here. First off, I don't want you to see this and get marred up in some complex math, because this is actually pretty easy. First off, so let's see if we can knock this out together. First thing I want to do is I want to see if I can determine the slope of this line. And so if I go back to just basic, graphing, basic math, the slope is defined as the change in y over the change in x. Okay, that's pretty basic stuff. Okay, so what can I say about the change in y and the change in x? Well, if I'm talking about this diagonal line, the change in x is 25 feet, right? That's pretty easy. So this is 25, all right? The change in y, what is the change in y here? I want to see if everybody's paying attention here. What's the change in y for this linear function going to be? So over 20 feet, how much do we change? Or over 25 feet, I should say. There we go. All right, 100. Now, Mr. Ashworth said negative 100, and he's right on that because this is a line with a negative slope, and we'll be able to draw some parallels to that in our problem here that we're going to do here in a second. So this line has a slope of -4, okay? So if the line has a slope of -4, then the question becomes, okay, what is this? How do we determine that length? Well, that length is simply going to be 25/4. And this length right here is going to be 75/4. And you can very easily test this out because if you take 25/4 plus 75/4, you're going to get 100/4, which is 25, which is the total length that it has to encompass. And so if you know 25, if you know the base of each of those triangles, then 1/2 of the base times the height will tell you the area under those curves. And we need that because we'll need to determine the area under the shear diagram to not only plot the moment diagram, but also as a check that our shears and moments are coming out correctly. Remember, when you're drawing whenever you're drawing a shear diagram and a moment diagram, you have to start at 0 and end at 0. The reason that the shear diagram starts and ends at 0 is because the sum of the forces in the y direction are 0. But the reason that the moment diagram starts and ends at 0 is because the areas under the shear diagram equal 0. The positive areas and the negative areas all sum up to give you 0. So that's definitely something that you need to watch out for. Any questions? All right. Okay, so let's look at the following problem. I wanted to use some point loads, but I also wanted to use some distributed loads. I wanted to try and mix it all up and come up with a problem that was challenging enough to give us something to work with, but was straightforward enough that we would cover not only the concentrated loads, but the distributed loads, so we'd cover everything, and this is what I've got. So I've got an overhanging beam. So when I use the term overhanging beam, that portion from C to D is extending beyond the support. So that 60 kip load that's at D, it's sort of akin to like a person on the end of a diving board, right? Because I mean, imagine how a diving board would behave, right? You've got that, the swimmer or the diver at the end, and so it sort of sticks out like that. The central span from A to C carries a distributed load of 3 kips per foot, and then I threw a 30 kip load right at point B. And I need to draw the shear and moment diagrams for this beam. And so just like before, I'm going to have to determine the support reactions, and then I'm going to have to plot the shear diagram, plot the moment diagram. It's a step-by-step process. So let me stop the share. Where's my... Make sure that's coming forward. Yep. Okay. So let's see. Okay. So let me make this a little bit bigger. Okay. So here's our problem. And so first thing I'm going to do is I'm going to identify some unknown reactions. So let me see if I can move this over. Let's move it over a little bit. Okay. So let's identify some unknown reactions. So again, point A and point C are going to contain those unknown vertical reactions. And so I'll name those AY and CY. And then support A is a pin support, so it contains a horizontal reaction that we'll call AX. But again, just like with the last problem, we can sum forces in the X direction. And we can see that AX is 0 because there's no horizontal forces anywhere on the structure. And whenever you're drawing shear diagrams or moment diagrams, really the star of the show is the vertical loads, because a shear diagram is all about your distribution or your change in your vertical effects. Okay, so everybody good on that? Hold on. Am I having some connectivity issues? My camera shut off on me. Is everybody still hearing me on the other end? My camera's decided to shut off on me. Okay. All right. If you run into some connectivity issues, I guess let me know. Okay. So we're going to approach this the same way that we've done previous problems. We're going to sum moments at A to determine the reaction at C, and then sum forces in the Y direction to determine the vertical reaction at A. So I'll go ahead and start that out. So I'll say the sum. Oh, let me use my button here. So the sum of the moments at A is 0, and then we'll take moments that way to be positive, and we'll chug this out. However, I do want to make sure that we're dealing with this distributed load right now, so let's go ahead and handle that. So I've got this distributed load, and it's 3 kips per foot, and the length over which it's acting is a total of 60 feet. Okay, so what I'm going to do is I'm going to idealize that as a single load right here. Now, can somebody tell me first off, let's handle the magnitude. What's the magnitude of this load going to be? How much is that load going to be? Anybody got an answer for me on that? So 3 kips per foot, and the total length is 60 feet. Okay, there we go. Yeah. Is everybody okay with that? Because that was a slow response, and I want to make sure that we're not rushing forward through here, right? So like if you have right, let's say you have 200 pounds per foot, and this dimension is 8 foot, right? So just think about it, you know, use some it's really just some common sense. If I have 200 pounds per foot over a distance of 8 foot, that's a total load of 1,600 pounds, right? I promise it's not a trick. You know, we're really, and again, all we're really doing is just saying, okay, what's the area under that load? You know, that's basically all we're doing. And then if you're okay with that, help me out with this. What's that distance right there? There we go. 30 feet. That's exactly right. All right, I'm going to erase this over here. I don't want that to be in the way of some of the work I'm doing later. All right, but is everybody okay on that? I don't want to rush through. We got plenty of time. Okay. All right. So let's. Okay. So here, let me just sort of look at it like this. Okay. So first thing we need to do is we need to just identify, you know, what's important about the distributed load. Okay. So here's the distributed load, and what do we know about the load? Well, it's 3 kips per foot. Okay. So what that means is that every foot, that is 3 kips, 3,000 pounds. So if, you know, let's say this was a foot, that would be 3 kips. And this would be another 3 kips, and another 3 kips, and another 3 kips. Every kip, or every foot, that's another 3 kips. Okay. And so the first question we have to ask is, how much is the total amount of load, like the total amount of force? Well, how long is the load? All right. So here's the load. It goes from here to here, right? So that total distance is 40 foot plus 20 foot, or 60 feet, right? So the load is it's 3 kips per foot, and the total length of that load is 60 kips. So the first thing we'll ask is, well, how much force is that? And so if I have 3 kips per foot over a distance, a total width of 60 feet, then that means that's a total force of 180 kips. Okay, so that's the first question we have to answer, and then the second question we have to ask is, where is that resultant going to be? Well, again, look at the shape. Okay, so here's the beam, and we're talking about a load like this. It's a rectangle, right? So where is the centroid of a rectangle? The centroid of a rectangle, if the rectangle is 60 foot wide, the centroid of a rectangle is 30 foot over, right? If this is 60 foot, here's the resultant, that is 30 foot, right? Does that make sense? So this dimension here is going to be 30 feet. Okay, and everybody else good with this? I mean, we got time, yeah. So don't let me rush through it if you got questions. Okay, good. All right. Okay, so now what we're going to do is we're going to determine the support reactions, and we're going to do this like we've done all the other problems, only in order to determine that support reaction, instead of worrying about this distributed load, that's what the 180 kips does. It says we don't have to deal with the distributed load because that 180 kips, that's 30 foot away from the support, that's acting as a substitute for that load because it's got the same magnitude and it contributes the same moment because we put it where the centroid is. So if we're summing moments at A, and remember, we're taking moments in this direction to be positive, okay, so let's take the 180 kip moment. So we have 180 kips. How far is that from A? Well, it's 30 feet. Now, at A, and I want everybody to help me out with this, is this generating positive bending moment or is it generating negative bending moment? There we go, negative, because it's rotating about A clockwise. Like put your finger at A and see how imagine that A is the center of the steering wheel, and if I put a F force, 180 kips, 30 foot away from the center of the steering wheel, how's the wheel going to turn? It's going to turn clockwise. Okay, so next comes the 30 kips. Okay, so we're handling these loads one at a time. So we've got that. Now we've got that. Okay, so 30 kips. All right, does that generate positive or negative bending moment? Negative. And then from A, how far is that from A? There we go. All right. Next, we've got our CY. Okay, so CY, that's the force. What the bending moment, is that positive bending moment at A or is that negative bending moment at A? There we go. And how far is that from A? What's the moment arm? There we go. And lastly, we've got the 60 kips. It's going to equal 0. Positive or negative? Negative. There we go. And the moment arm. There we go. 80 feet. That's what I like to see. Good. And if anybody has any questions about this as we move on, you let me know, okay? I'm going to erase these. Okay. Okay. So now this just becomes an algebra problem, okay? So 180 times 30 is, this is minus 5,400 minus 30 times 40 is 1,200 plus CY times 60 minus, and then we have 60 times 80 equals 0. Okay, so let's see if we can simplify this a little bit. Let's move the CY over here. And then 5,400, 1,200, 4,800. That's minus 11,400. So can somebody tell me what CY is going to be? Just looking at this. I just want to make sure everybody's paying attention. Positive 190. And when we say positive, just as Mr. Ashworth said, that's 190 kips going up, okay? All right, so that's one of our reactions right there, 190 kips going up. Anybody got any questions on that? Okay, all right. Now what we got to do, we have to sum forces in the y direction, right? We've summed forces in the x direction, we've summed moments. Now we need to sum forces in the y direction. Okay, so let's sum forces in the y direction, all right? So this one's easy, right? All we have to do is take all the upward forces as positive and all the downward forces as negative. So I got that, and that's going to be positive, and I've got that, and that is going to be negative, right? So what do I got? I've got AY plus CY minus 180 kips minus 30 kips minus 60 kips is 0. All right. I'm going to scroll down a little bit. I'm running out of room here. So AY plus, and then we've got CY. We figured out what CY was. CY is positive 190 minus, then 180, 30, and 60. That's 270. So therefore, and that's equals 0. So therefore, AY is what? What's AY got to be? There you go, 80 kips. Okay, let me move these circles because I'm going to keep using these. And I'm going to cheat a little bit and copy this image over again. But before I move on, does anybody have any questions? So just so we're clear, this is 80 kips, and this is 190 kip. All right. And I'll give everybody a sec if you need to redraw some things or you need to plot some stuff out. Take your time. We got plenty of time. I don't want to rush this because this is such an important concept in engineering. All right. If you need me to scroll back up or take my time, let me know. I don't want to rush through this. Okay. So we've got our reactions figured out, and so now we're ready to start drawing our shear diagrams and moment diagrams. I'm going to start, you always start with the shear diagram first and then move on to the moment diagram. So I'm going to do the shear diagram. Now, one of the things I'm going to do is, so I'm going to do what I did before. I drew that, horizontal line. That's sort of my baseline. And we said this is the shear. And it's going to be in kips. Another thing I'm going to do to help me out a little bit is I'm going to do this. If you notice what I'm doing, I'm kind of drawing some guidelines that go along the plot. And this is just so that I can sort of track like where values are. It's just a little visual trick to make it a little easier to track. Another thing I will point out, okay, and this is probably one of the most important things I really want to make sure that you're clear on. If you recall, up there I had that 180 kips right here. I had that there. Here's the thing. That does not exist on the real beam, okay? What we did is we placed that 180 kips there as a representation of this distributed load. And we did it to make the reaction computation easier. But what we're doing here on the shear diagram and on the moment diagram is plotting the actual shears and moments resulting from the actual loads on the beam. So once you're done with the reactions, that 180 kip load we put there, that kind of needs to be erased from your memory. It doesn't exist. All right? Just make sure that you get rid of that. And one of the ways that like when I was first learning this, I would just redraw the beam from scratch all over again. That's kind of what I did here. I cheated a little bit and copy and pasted the image, but you get the idea. Okay. All right, so we're going to start at 0. And so just like before, we're going to jump up to 80. Okay, just like before. So we have, you start at the left, work your way over to the right. And so the first thing you see is that jump up to the 80. Okay, everybody good on that? Now, I need some help. Okay, so we're going to take this alphabetically. We're going to start at A, work to B, and then work to C, work to D. So let's go from A to B. Now, I'm going to need chat's help on this. Help me out. From A to B, how much force is that? $120. Now, that's exactly right. Okay, 3 kips per foot over a distance of 40 feet. Okay, so that's 120. All right. Now, here's the first thing I want to do. I want to recognize that if I start at 80 and I'm going down, right? These are downward forces, and I'm going down 120 kips. That's going to put me at -40, right down here. How do you make that trek? Linear, constant load, linear shear diagram. So that'll look something like this. Let me see if I can draw this out without being too sloppy. Boom. That's going to be the shear diagram in this region, and this is -40. Now, what happens right at B? I want to see if everybody's paying attention. If I go from, so I started at 80, dropped down 120 to -40, what do I do next? Go down 30 more immediately to 70 or -70. So maybe I'll clean this up a little bit and I'll say, okay, this is -40, this is -70. Okay, So anywhere you see that distributed load, that's going to be a linear pick. See, think about it like this, like a concentrated load, that's an abrupt change in shear, right? You're putting, 30,000 pounds right there at that one point. That's a sudden jump. But this 3 kips per foot is a little bit more of a gradual change in shear, hence why it's a line like this. Okay. Now, I want somebody to tell me, if that's the case, what I do from B to C. Somebody in chat tell me, like, what am I going to do in this region? What do I do there? I go down 60. And so where does that put me at? If I'm at negative 70, where am I going to end up at the end? No, not negative 100, negative 130. There you go. So, and that's going to look, oh, maintain my color scheme. Negative 130. All right. And now what do I do? I'm at negative 130. What does the beam tell me to do? Up 190. And up 190 to where? If I'm at negative 130, there you go, 60. So that's going to put me at 60. Now, what does the shear diagram look like from C to D? Flat. That's exactly right. No load. There's no load in this region. So if there's no load, there's no change in the shear diagram. And then what do you see there at D? You see a 60 kip load brings you back down to 0. Boom. There's your shear diagram. All right. Let me take a sec. Let's see if anybody has any questions. I'm sure we've got some folks copying this down, so I want to make sure that this is clear. All right. Okay. Now that we've got the shear diagram, we need to draw the moment diagram. And in order to draw the moment diagram, we need the area under the shear diagram. Now, this might seem a little strange. I'm going to start at the right and work my way over to the left because it gets easier, or it's easier on the right. Here's what I'm going to do. I'm going to split this up into 4 regions. Okay, so we're going to say, this is region 1. This is region 2. We're going to take this as region 3, and this is region 4. So I'm going to start at the right and work my way over to the left. So somebody help me out on region 4. What is the area under the shear diagram in this region 4? And what I'm talking about this shaded area right there. What is that area? Nope, not 120. It's 1200. There you go. And I liked what Mr. Ashworth said, because it's foot kips. Because we're taking the area under the shear diagram, so it should be in moment. It should be in foot kips. That's exactly right. So this is positive 1200. Okay, that's exactly right. All right, now let's talk about region 3. Now, if you want, you can split this up into, like a 3.1 and a 3.2, like if you want the area of that triangle and that rectangle. But really what I'm after for this region, I want all of this. I want the whole thing. What is the area of all of that? Like if you had to add up all that area, I want somebody to help me out and tell me what it is. And I'll show you a couple ways that you can compute that here in a bit. But does somebody have an idea of what this area is? Maybe one way you can figure that out is, what's that distance? All right, negative 2,000. I want to see if I get a second on this. Anybody got a second for me on that? There we go. Good. That's what I like to see. All right. That is exactly right. Okay, this is negative 2,000. Oh, I want to use my color scheme here. So this is negative 2,000. I want to show you a couple ways that you can go about this. Okay, so first off, there's two ways to do this. Okay, the first way to do it is, I think, probably what you would think is the, and somewhat obvious way is to say that this is 60 and this is 70 and this is 20. And so you'll say the area is 70 times 20 plus 1/2 60 times 20. And that'll give you 1,400 plus 600, which is 2,000. Okay, that is one way of doing it. Another way to do it is this. Okay, what you can do is you can say, I tell you what, I'm going to take this and I'm going to put it right there. Right? And so instead, what this is going to look like is it's going to look like this. And so really all I'm finding is the area of a rectangle that's 20 foot wide, and the height is the average of 70 and 130, which is 100. So the area is 20 times 100, which is 2,000. And so there's a couple of ways of going about this. You could do it either way, but either one works. The second one is the area of a trapezoid, because that's basically what it is. Okay. Everybody good on that? I don't want to skip past stuff. We got plenty of time. Okay. All right, so I'm going to move this down. I don't want this to take up space. I don't want to delete it because I think this is good for reference, but I don't want that to take up space. Okay. Now, we need the area of these two triangles. And this goes back to the same problem I was mentioning earlier. So we need to know this dimension here, and we need to know the similar dimension up there. Okay. Now, first thing to keep in mind is that this entire width is 40 feet, right? So we're talking about this dimension right there, right? So these two distances have to sum up to be 40 feet, okay? Now, what we're going to do is it's really simple. We just take 80 and we divide it by something. What are we going to divide it by? We're going to divide it by the slope of that line. What is the slope of that line? What is the slope of that line? It's -3. And you want to know where you get that slope? Right there. Because the slope of the shear diagram equals the load. Okay, so this is 80 over 3, or I think it's like, yeah, 26.67. and this is 40 over 3, 13.33. And when you add up 26.67 and 13.33, you get 40. So that should ensure that, you know, that everything matches up. Now, if that's the case, somebody tell me the area of this region. Somebody tell me region 1. What's the area of that going to be? I guess I should put here 3 kips per foot. Anybody have an answer for me for this first area? That's exactly right. That's exactly right. Yeah, so this is positive 1066.67. And if that's the case, what's the area of this little triangle, the one that's left over? There you go. And just here off to the side, here's our 4 areas. If you sum up those 4 areas, you get 0. Or let me do a little better on that 0. And that should be a check that your moment expression is correct. Okay, speaking of, we're running down to the wire, so let me see if I can knock out this moment diagram really easily. Because once you've got all the areas, the moment diagram is actually really easy to draw out. All right, so moment diagram. Now, what I'm going to do here for the moment diagram, I'm going to draw these little guidelines, you know, down. But I'm actually going to draw one more. I'm going to draw one right here. Because that's where that, you can see where the shear diagram kind of crossed. I'm going to draw that one because I kind of need that one too. All right. Now, what I'm going to do first off is, you know, look, before we talk about the shape, let's look at the values, right? So watch this. So everybody, before you start copying along, just watch with me, okay? So this is, we're going to start at 0, okay? And then what we're going to do is we're going to jump up, and this is going to be 1066.67, because now what we're doing is we're looking at the areas, right? So I start at 0, I go up 1066.67, then I'm going to drop 266.67, and that's going to put me at 800. And then I drop down from 800 another 2,000, and so that puts me at like minus 1,200, and then the positive 1,200 brings me back up to 0. Okay, so and how did I do that? I was looking at the areas. Okay, so I'm just following the areas, you know, and I'm saying, okay, you know, jump up 1066.67, then drop down that much, drop down that much, drop or raise up that much. So start at 0 and end at 0. The thing that you got to pay attention to, though, is the shape. Okay, so I really want everybody to pay attention and watch me on this. Okay, so let's look at this first shape. Okay, see how the shear diagram kind of looks like that, right? And so see how we have like a lot of shear to a little shear. See how the magnitude decreases? If the magnitude decreases like that, what that means is that your slope decreases. So you go from a lot of slope to a little slope. right? And that's going to be your shear diagram or your moment diagram value right there. Similarly, if you look at the next region on your shear diagram, see how it goes. So see how that triangular region, you go from a really, really tiny value of shear to a bigger value of shear. So see how, you know, I'm looking right here, how the shear diagram goes from a little to a lot. So we're going to go little to a lot. I'm sorry if the line's getting a little wavy on me. It should sort of look like that. What we're trying to draw here is a parabola. That's the best parabola I can draw. My art skills are horrible. Same thing here. The magnitude, you can see how the magnitude decreases. So the slope should go down. It should go a little to a lot. Little to a lot. Okay. The only region on the shear diagram that is a line is this last one. We have that stair step sort of constant shear. So this is a line, right? And so much so that I'm actually going to put that on here, linear. And this is parabolic. Everything else is parabolic. The only thing that's a line is from C to D. Okay, are there any questions? Does this make sense? So what you're doing is you're going, you know, you're taking the magnitude of the shear and going, you know, a lot of shear means a lot of slope. Little shear means little slope. And see where we had a constant shear, we had constant slope, hence why that was a line, because a line has a constant slope. I want to give everybody a sec to see if they have any questions on this. Any questions? All right, everyone, it's 1:52. I guess I'm gonna have to call, and I know some of you have class after this. I hope everybody has a wonderful weekend. I've got a practice problem, and for your homework, the homework I think is easier than this one. I didn't want to make it too challenging. So if you can handle this, you can certainly handle the homework assignment. Monday's exam review. Come prepared with questions, everybody. That's all I have. I will see you all Monday. Y'all stay safe, stay healthy. We'll see you then.